We'll explore later on in the webinar. And then lastly, we'll dive into some of the statistics and specifications in a little while. But just to even keep a single GPU fully utilized requires a lot of storage bandwidth. It's like we've taken another leap forward in computer architecture. And what it's causing us to do is have to rethink just how we store data and how we can get it to and from an AI system. So let's briefly touch on some of the types of data that need to be held for the average AI system. So raw data is kind of self-explanatory, but if you think about it, it could be lots of unstructured content, video, audio, text, emails, things from like live chat, internal messaging systems, and it can stretch to other things like telemetry from IoT devices to autonomous vehicles. So there's a huge volume and it's not very well structured. Then training data. So this is kind of the next step in an AI process. We've gone through some level of organization. We've kind of cataloged a bunch of data, and then we can use that for things like pattern matching. So, imagine you're training a model to recognize number plates or license plates on cars. So it's kind of essential that you have examples of the images that a system might see when it's trying to identify that particular object in the overall image. So that training data is kept and it's preserved for reuse and reevaluation over time. And then that way we can look at the efficiency of a model, we can tweak and tune it, and then we can retest against the same training data, just so that you can see if the model has improved, the model has got worse, those kinds of things. And of course, if you use a new set of training data, you wouldn't yield a fair test. So we kind of have to keep those training data sets around for a reasonable amount of time. Then, of course, the models themselves, once created, we need to keep them somewhere. So if you think about just how long some of these it can take for some of these models to be created, it can take weeks. So of course, we need to provide some very reliable storage so that they can be stored for future use and called upon when needed. And then finally, after you go through all of these steps and all of this sort of transformation of work, um, we end up with a bunch of results. We've if we go back to the license plate example, we've identified a number of license plates. We can extract that data. We can use it in some other business process where it's needed. Um, this these models have to be then enabled, or the results from a model has to be enabled or has to enable a business to then be able to make decisions, follow processes, and actually put them to work. So what makes AI storage needs special? Let's take a look at NVIDIA's H100 GPU. From a sort of a compute perspective, a single card can peak at 4 petaflops. Um, but what keeps us probably more interested from a storage point of view is really when you think about how much data it needs to stay highly utilized. So to feed it and keep it happy, we need to provide a sustained stream of 5 gigabytes a second. So that's it's quite an ask for a single card. But then you start to think about what does a deployment actually look like, and we'll take a look here at NVIDIA's DGX H100 system. This actually contains up to 8 of those GPUs. So now just for this one system, we need to be able to provide 40 gigabytes per second, just to make sure that this particularly expensive hardware is kept well utilized and busy. And this kind of model does also apply to other hardware as well. It could be any other server vendor that provides a system that can have up to 8 GPUs in there. The GPU requirements don't change between these different systems. We really just have to keep feeding the system lots and lots of data so that the hardware's highly utilized all of the time. But then if we take it a step further, and this is perhaps where it gets quite eye-opening, when you think about some of these larger scale cluster configurations. So this is NVIDIA's SuperPod approach. And in that image there, what you can see is 8 cabinets. Each cabinet has 4 DGXs, each with 8 GPUs in there. So just across these 8 cabinets of compute equipment, that's 256 GPUs. There are other models that scale even further to potentially take the the IO challenge to a yet another level. But just to keep this kind of environment highly utilized, we'd be looking to have to provide around a terabyte per second of data into this kind of environment. So it's like it's a whole new world of how do you just how do you get that much bandwidth from a storage system into a compute system? And one of the good things about all these kind of configurations, we can also add in sort of caching elements and things like that. So in the DGX approach, within each node, there's a bunch of local storage available as well. Because of course during training you do a lot of reread as well. So having like a local cache means that you always, you don't have to reach out to the external storage system. You can just read locally, which obviously is way faster. So really, the job of a storage system in this kind of environment is just to feed the GPUs. The compute power is high and it can process a lot of data. We've just got to get that data set to the GPUs. And of course, the results back into a storage system as fast as possible, just to keep everything ticking over efficiently. So what can we do in the storage world to keep up? So let's go back to the basics. So whenever you build any kind of system, there's kind of four attributes that you really have to have to balance, sorry. So if you think about performance, what is the requirement? What does the application actually need? So here we're looking sort of at the theoretical maximums of these kind of pieces of hardware. It may not be the case that you actually need to hit those peaks, but that's kind of, that's working out what the balance is. What is the business requirement? How quickly does, an AI job have to run and complete? What's the throughput required for ongoing use of those models and that kind of thing? So you have to really understand what the overall system actually requires. And then in capacity, like how much data does an application need to store? How much will it grow? How quickly will it grow? When do you need to decide how you'll scale the system? Those kinds of things. Reliability. What kind of failure scenarios can be tolerated? Maybe we can think about trade-offs where we can reduce cost by being less reliable. Think about that local cache. Doesn't have to be protected because the source data is in a protected storage system. So that there's one area you can sort of trade off there. Or is the data hypercritical? It can never be lost. You need to then start thinking about, do I have a primary storage system that then replicates to a secondary site for redundancy reasons as well. And then finally, the one thing that always is in our minds is around cost. We obviously have to take that into consideration. We could easily build the fastest system on the planet, but if the specifications of the system, its capabilities just exceed what's needed to get the job done, it's kind of a poor financial decision. So we have to balance all of these things to build something that actually like, is fit for purpose. So as I mentioned at the beginning of the presentation, and I just kind of want to reiterate it, the consumption of storage, really only has one direction. Once used, end users rarely ever release storage that's been allocated to them. And with more and more data being generated every day, we've just got to work out a way of keeping up. So let's think about storage system architecture. So this is, the storage system itself, not so much the networking components. It's how do you piece together a system? And they kind of fit into two groups. So firstly, the scale up. It's fairly typical for proprietary systems. You start with a head node. You need to grow, so you add like another disk tray or disk shelf, and eventually you keep on growing, you keep on growing, you keep on growing, and you reach the maximum capacity of that system. You haven't increased the performance of the head throughout all of this. It's the same head just with more disks behind it. Once you reach the maximum capacity, then the only natural thing to do is go and buy another storage system. So then you kind of have to integrate that. So then the other approach, and this is more common in sort of distributed systems, is the idea of scale out. So each time you start with a cluster as a single node that contains sort of CPU, RAM, storage capacity, and then as you add another node, you scale out. So you then have every time you grow, you increase both the resources within the cluster, but then you also add capacity as well. And the great thing about this is you get pretty close to near linear performance improvements as you add more and more nodes into the system. Um, you don't have this sort of, like fixed performance that can never, never grow like you would in a scale up type system. So in kind of a comparison, scale up systems are kind of limited to the maximum performance of the head or the controller, whereas a scale out system adds both performance and capacity in each and every upgrade. In terms of capacity, again, that scale up system is kind of limited to the maximum number of slots for disks. There's only so many trays you can put on a bus. There's only so much bandwidth an individual bus has. So, at some point you're going to run out of capability in that system. Um, Whereas if you think about the scale out system, theoretically you can almost grow to kind of limitless capacity because every time you're adding performance as well as adding storage space as well. The thing to consider there is, of course, you have to think about, operationally, how would you grow out a system? You have to think about in a data center, as soon as you start having network traffic traveling sort of east and west across the data center, the average bandwidth per machine obviously decreases just because of the way that you have sort of aggregation layers in the network. So you do have to put quite a bit of planning and forethought into how you will grow and how you will deal with having enough bandwidth within the system to manage all of the internal replication, those kinds of things. So it's definitely, a scale-out system is definitely more complicated, more complex. But if with reasonable planning and sort of forethought of how that will all piece together, it's definitely a viable way and probably the only way you can really keep up with some of the growth challenges that we see. I think lastly, one of the sort of killer features of open source scale-out systems is the fact that you can just use off-the-shelf hardware. You can kind of mix and match over time. What server you would buy today is not going to be the server you're going to buy in 6 months or 12 months. Just look at things like the availability of flash devices, SSDs, NVMe devices. What's available today is just not available in another 6 months from now. So having the ability to mix and match these different pieces together in a single system and abstract it with software definitely provides you with a nice sort of future path to grow and not lock yourself into a specific vendor and the parts and components that they can supply you with. So let's drill a little bit deeper into how you go about building a scale out solution. So there are kind of three areas that we really need to care about. So within the within the servers that we would use, we really need to think about two main components, I guess. So that's the CPU and the RAM. Of course, the higher the clock speed really does help with some of the components within Ceph. And also sort of matching the number of CPU cores to the number of disks and the type of disk. And we'll go into a little bit more detail about that in a few slides' time. The second area, of course, I mentioned this already, it's the network. It's having plenty of bandwidth and keeping the latency low. Within the storage system itself, you're going to replicate data across nodes for resiliency reasons, but then also you need to think about how does that data get out to the actual user or the use case, the application. And then finally, the disks that you choose for the system. We can start thinking about how do you match the needs of a data set and the workload to the capabilities of the underlying storage media. So be it flash, be it spinning media, or in some cases we'll mix and match to use flash as a caching mechanism, or we'll create different tiers of storage within a single system. And then to look at this from another perspective, when you start thinking about some of these large scale applications, how you actually use a storage system can really drive efficiency. So let's take a look at the first example here. So if you think about sharding of data, so you have a data set. Let's imagine it's an S3 bucket. So you could put all of your objects in that single bucket. That's it's a permitted operation. At the end of the day, it's a put operation, and then to make use of them, it's a get operation. But just imagine from a metadata standpoint, we record permission information about objects, um, size information. We tag them with all of this metadata, and that has to be stored somewhere as well, right? So if you have a bucket with billions of objects in it, and then you decide that you need to list every object in that bucket, you're obviously going to send this metadata request to the storage system. It's then going to walk the entire bucket and provide you with all this metadata. So then we kind of run into this is a slow operation. It takes time. And what is really a better approach is if you start thinking about how can I divide up my data, just with simple logic. So, like as a really basic example, and it's not perfect by any means, but it's kind of straightforward. If you've got objects that start with the letter A, they go in the bucket called the A bucket, the B's in the B bucket, the C's in the C bucket, and so on. And then that way you have a bunch of different buckets containing the same number of objects, the same amount of metadata, but that metadata is then in a smaller amount per bucket. So that makes things a bit more performant when you do those things that are metadata heavy. Another area, and I mentioned this already, is around tiering of data. Um, so again, using some kind of human logic, which data sets are the most important and they require the fastest storage, which data sets are less important and can be put onto sort of lower cost capacity optimized storage. Think about the books in the image there. The books that you don't read very often go on the high shelf. It's hard to get to. It's like slower to get to. Whereas the books that you would access more frequently, lower shelves, straight in front of you, you can grab hold of them really, really easily. So again, sort of human logic, working out which pieces of your data need to sit in these different tiers. And then finally, as I mentioned earlier, this idea of caching. So there's of course lots of different places you can do caching. We can do caching within a storage system. You can do it in locally in a compute node or GPU node. So that you don't have to transit the network a bunch of times. Or in the case of the storage system, you don't have to hit the disks each and every time if you see a large number of sort of rehits of a particular object, or a file in a file system, or blocks of a block device. Another interesting area around storage, and this is perhaps where I start to bring in some of the Ceph specific pieces actually, is really around security and the things that you can do to secure the data that you have in the storage system. So firstly, in-flight encryption. It's still really quite important to have this enabled, even within a private data center with private networks. Really just to guard against things like eavesdropping. Especially when you have very sensitive data, something that's personally identifiable, medical data, financial information. It's still very important to make sure that that's encrypted while it's in flight. Um, the storage system itself needs to support some kind of client authentication, so that users with the correct permissions have access to some or all of the data sets held within the system. So in Ceph, we use this protocol called CephX, and that can also be sort of extended to integrate with external LDAP. So you can use that to manage like file shares. You can use it to manage who has access to buckets, even permissions to create buckets, and those kinds of things. And then lastly, it's super important to think about hardware failure and disk failure. In any kind of large storage system, it's going to happen during the life of the storage system, that a disk is going to fail. You're going to have to remove it and send it back for replacement to the original supplier. And by enabling at-rest encryption, of course, when that drive fails, you can just send it straight back. You don't have to worry about will somebody be able to recover data from it. The keys to unlock that drive are stored within the storage system. There's nothing in the drive that would allow that data to be unlocked. Even if it's repaired to a point where it's functional and you can read data from the device. So let's dive into Ceph a little bit more. You know, we're big believers of Ceph. We you know it's very much seen as the leading open source scale out solution. So yeah, let's see the different areas or the different ways we can apply it in these kinds of environments. So just going back to school a little bit. So what are the benefits of Ceph? As the underlying architecture of a Ceph cluster allows a user to start with something that's relatively small. I'm going to show a demo shortly, and you'll see just how small we can start a Ceph cluster, and then we'll talk about how it scales up. Um, and over time, you can add additional nodes to grow the cluster, depending on business needs and sort of requirements there. Um, the other thing that's super important about any kind of storage system is obviously reliability. Ceph's number one goal really is to keep data protected. So every write's fully synchronous. Every replica is created in a fully synchronous fashion. Um, yeah, I mean, for any kind of storage system, just being reliable and ensuring that once something is written to that system, it's persisted. And it's held there safely. And Ceph's number one goal was even from the very early days of Ceph being created, that was its number one goal. The flexibility of a Ceph cluster is awesome as well. You can create just that a single cluster that serves multiple different needs. So how you have you can mix and match different types of disks to create different types of storage pools. And then you can create things for high performance, things for or you can create pools for uh, archival type use cases as well. In the same system, you don't have to have different systems to do these things. And then in that single cluster, you can serve both. I say both. There's three things you can serve. You can serve block, you can serve file, and object storage needs as well. Again, you don't have to have three different clusters. You can do all of these things from a single cluster. Of course, no storage system would be useful if it can't go through an upgrade process without interruption, and that's absolutely possible within Ceph. Um, I've already talked about the security aspects and all of those things that I mentioned. That they're available within Ceph. The idea of in-flight encryption, at-rest encryption, and then as well as the sort of strong authorization. I think finally one of the things that sometimes gets missed when thinking about a storage system is actually the operational side of things. So from an operational expenditure point of view, the idea that you have this system that's self-monitoring and has a lot of self-management. A drive failure is not something you have to really worry about. Um, during a working week, you can wait for a number of drives to fail, and then go in and do like a bulk replacement, because all of the data will be redistributed across all of the nodes within the cluster automatically. And from a CapEx point of view as well, this idea of using off-the-shelf hardware, mixing and matching over time, again, has a really good sort of financial perspective as well. So just a quick recap of what a cluster actually looks like. So over there on the left side, the Mons and the managers, they are the Mons are kind of they're mandatory. They are the manager of the storage system. They look after the overall cluster state. They create a map of where disks are within the system, in which kind of nodes. They look after making sure that the replication happens, that scrubbing happens. This idea of ensuring data integrity at all times, and they also look after all the auth pieces as well. At the bottom of this diagram, we've got the OSD nodes. So they're actually like the storage servers that contain the SSDs, the hard drives that hold data. In this diagram, I've sort of spread them across like three stacks. So if you imagine those as availability zones in a data center, it could be a rack, bunch of racks, and then that way, if you lost, say, an entire rack of the servers on the left side, you still have two other availability zones remaining where your data's still safe and and available. The manager is a component that tracks the performance metrics of the cluster and then provides it through a Prometheus endpoint to either something like the Canonical Observability Stack, or any other sort of monitoring tool that you might have. And then we have a bunch of different ways of accessing the cluster. So Ceph's block storage protocol by default is RBD. So that's the RBD clients. They communicate directly with an OSD node. For object storage, the S3 clients in this diagram, they make use of a gateway essentially that provides the HTTP endpoint, and then accesses into the Ceph cluster and stores the data natively across the Ceph cluster. Those don't have to be physical machines; they can be virtual machines or LXD containers as well. And then finally, for the file system clients, they have like a two-path approach into the system. So any kind of metadata operation goes to what we call the metadata server, but then actual like read-write I/O traffic goes direct to the OSD nodes as well. And then that way you get the benefit of being able to talk to every component within the system, rather than just hitting that one gateway or multiple gateways. It's not shown here, but we also do support iSCSI block access as well via a different gateway, and then in the future we'll be adding another gateway for NVMe over Fabric as well. So let's think about, or let's just go through these ideas of what kind of hardware we typically use for different scenarios. So if you think about a performance requirement, so the best possible performance you get out of an NVMe device, that's something where we need a lot of compute within a storage node, but relatively few NVMe devices. The NVMe devices themselves are super fast, so really it's about having lots of CPU cores to drive them hard. So those kind of smaller nodes, we normally see configs around like 64 terabytes of storage within a single sort of one U chassis. And then when we start thinking about more general purpose, so this might be like, VM boot devices, kind of that virtualization workload. Typically we see, or we kind of recommend a larger number of NVMe devices, but not necessarily scaling up the number of cores. You're not going to drive those devices super hard, but you're going to get very sort of consistent performance across that kind of system. And then finally, the capacity offering, or the capacity approach. That's really, something that's like a great building block for like a data warehouse or a data lake. This idea where you have like sort of 20 NL SAS devices. You think the most sort of, or the largest capacity these days around 22 terabytes. So that's kind of like a 2U chassis with 440 terabytes of storage within it. So that's a really good scalable building block. Still with a reasonable amount of compute power. We don't recommend um, sort of cheaping out on the amount of compute you put into like a capacity node. It really does make sense to still have a reasonable amount of compute in there. Then you can co-locate some of the other services like the Rados gateways, MDSs if need be, those kinds of things. They don't have to be in separate nodes. Across these configurations, there's obviously variables. We can change out sort of the networking components. We recommend minimum of 25 gig Ethernet. Of course, for some of these use cases, and especially as you look at the AI side of things, going up to 100 gig Ethernet actually makes a huge difference, especially when you think about some of the capabilities of the GPUs and the amount of throughput they need to run optimally. And then we can also do things around especially like in a capacity sort of configuration, we can start thinking about adding in Bcache as a way of providing a flash cache in front of every OSD. So that's one way of sort of eking out a bit more performance from the system as well. Uh, as I mentioned, we kind of normally try and keep services co-located on the OSD nodes, but sometimes there is a reason to break these out. So take the Rados gateway. It can be a really good network boundary as a physical device. You have access into the storage cluster, and then you have the sort of front end facing out into the rest of the data center, so you can use it as a good boundary that way. And then for very high throughput um, file system workloads, we find that a dedicated MDS really does help, again, get the best performance. And really, it's around the metadata operations. So it's not, it's computationally difficult work. So it's best to, um, provide sort of high clock speed CPUs to do that specifically. Whereas within the cluster itself, you don't necessarily need to go to, super high clock speeds. So how do you get started with Ceph? Um, all of these things that we've kind of talked through sound like you've got to do sound kind of complicated, but I want to highlight like just how easy it is to get started with Ceph. So let's take a look at MicroCeph, and uh, just to be super clear, micro doesn't actually mean small scale. I mean, it can be, and the demo I'll show will explain that. It really does mean micro operations, low overhead. It's simple, it's straightforward, it's repeatable if you need to deploy in small scale environments, yet also scalable enough to work in large scale environments. And I'll talk about that in a second as well. It really is just Ceph made easy. So when we created this approach around MicroCeph, it's really for that non-expert kind of user who need reliable deployments in all kinds of environments. From that dev use case to CI to edge, and then even into large scale production, like we're talking about for AI. The idea is that deployments are just a few commands, data operations like scaling, replacing drives. They're also super simple. MicroCeph itself is delivered as a snap, so all of its dependencies are included, and it runs fully isolated from the underlying host. By using channels as a delivery mechanism, we can have multiple different versions of Ceph. So right now we have Quincy and Reef as the most recent versions of Ceph. Um, and just remember, there's nothing micro about Ceph. It's still upstream Ceph is just in lightweight tooling with minimal deployment uh, complexity. So what does MicroCeph give you? Well, it's Ceph. So you have block storage, file storage, object storage. Um, it's just available in a super quick, ready to go, easy to use tool. Um, and then in terms of scalability, with MicroCeph, we've been doing some testing, which took us up to 84 nodes. So imagine that capacity tight approach, 440 terabytes per node, 84 nodes. That's over 35 petabytes of raw storage. That's big. It's not micro. And then as you scale up from a few nodes to many nodes to racks of nodes, MicroCeph will automatically adjust crush rules. So that will make sure that you have the best sort of protection of data across the different configuration. As you start scaling up into more and more nodes, it becomes more useful. We built in support for separate Wallen DB, so um, that gives you a write-ahead log, and also hosts the database that's used for each OSD. So this is most important for those capacity kind of configurations. For Flash only, it doesn't really matter. It's best to keep those devices on the same drive. And so here it is, with just these 4 commands, you can get up and running with a minimal Ceph cluster. First, we install the package from the Snap store. We bootstrap the cluster, and that creates a single mon, brings the cluster to life. Then we start adding disks to this particular node. So what we're actually doing here is just adding some simulated drives, just as a test or a quick demonstration. In the longer demo that I'll show shortly, we will actually add real devices into the Ceph cluster, and then just finally with a Ceph -s, you can then verify the cluster status, see that you'll have a pool created, and the various daemons running to provide the different types of storage. So with that, let's hop over to this demo. All right, so we've got 3 virtual machines here. And what we're just going to do is install the snap. So we just got success back from all of those 3 VMs. And then we'll hop onto the first one. So we obviously need to bootstrap the cluster. So we will do that from the first node. And then we want to start adding other nodes to the cluster. So of course there's VM1 and VM2 there available. So what we've done is just told the first node we're going to add these 2 other nodes. We've given the node name, and that gives us this key that we can then use on those other nodes to automatically join the cluster. So we've done that for the first one, and now we're just going through the second one. So then we go back to our first node, and let's take a look at the status of MicroCeph. So we can see that there's no disks, but the virtual machines have been added to the overall cluster. So you can see that Ceph is complaining. There's only there are no OSDs, so it's in a 1 state. But you can see we've got 3 mons up there spread across all the 3 nodes. The manager is currently running on node 0. And what we're doing here now is we're just telling each node to add a disk into the cluster. So you can see that now that we've got disks, we've automatically created a pool for some of the metadata stuff that's required within Ceph. And now we want to add object storage capability. So we'll add Rados Gateway just onto the first node. So there you can see that the service has been added. And you've got the MDS, Manager, Mon, Rados Gateway, and OSD. Whereas on the other nodes, we don't have the Rados Gateway. We just, it's a quick demo. We don't need to add it everywhere. So what we just did there rather quickly was create a bucket user or an object storage user. And that then allows us to interact with the Ceph cluster from an object storage point of view. And in this case, we can upload a file into the bucket. And then we can see just quickly there at the end that we've added some files into the object storage bucket, and then we can obviously then interact with those. So it's a really quick demo. It's literally 3 minutes, and there's a lot of sort of still manual work in there, just to walk you through the different steps of the demo. Bring my video back. So yeah, there's a bunch of sort of manual steps in there, but it still only takes you 3 minutes to build a 3-node cluster with some OSDs in there. MDS is enabled, so you have file storage. The OSDs provide the block storage via RBD, and then also just adding in the Rados gateway, so you can have object storage configured from that single cluster. So, and that kind of brings us to the end of the webinar today. Connecting this idea of a scalable storage system with really scalable demands of GPU compute for AI are 2 concepts that I wanted to bring together. And just sharing this idea that you've got MicroCeph and you can try it and use it and play with it on a very small environment, but it also then does scale out to those kinds of requirements that we've been talking about. So I hope it was useful. And not just the idea that it's good for AI has been shared. It's also useful for lots of other different other storage requirements within the IT world. And if you want to find out more about Ceph, absolutely hit ubuntu.com/Ceph. All of the product information's there. Our documentation's there. You can find the guide to try MicroCeph out yourself. There's lots of great information there from the team. And so with that, thank you very much for your attention. What we'll do now, we'll just change screens a little bit, and we'll start going through some of the questions that we can see in Q&A. And yeah, let's have sort of an open discussion. And as always, the mute button got me. So what I was just saying is there's a handful of questions. And what I'll do is I'll try and organize them into sort of similar areas. I've just been sort of trying to keep some notes just on the side, so I can be somewhat organized, but of course then still miss the mute button like every time. So some questions around sort of automation and managing of infrastructure. So the first one, this is a common one we get. What about Ceph ADM? So Ceph ADM, of course, it's part of the upstream project. It's a great way of deploying a Ceph cluster. It's one of the options. It's great for a standalone Ceph cluster, but then if you think about it, you've got other pieces of tech in your infrastructure. If you're using something like OpenStack, you might want to use the same tooling to manage OpenStack as well as Ceph, or to manage Kubernetes. And so Canonical, our like tool of choice is a project called Juju. We basically take all of these different pieces of software and wrap them up in what we call charms. So what's interesting here is when you start looking at something like MicroCeph, that looks very standalone in the demo. And of course, it can be standalone, but what we can also do is wrap a charm around that. So that's called charmed MicroCeph or charm MicroCeph. And that's just one way that you can then start to interact with the other applications, be them infrastructure, be them higher level things consuming something like an S3 endpoint. So, I think it's fair to say that there's not always the one perfect choice for everybody. So here at Canonical, we do provide a level of support for things like Ceph ADM, even for Rook on Kates. We provide rocks, which are OCI compatible images that can be used with those tools. We obviously have, the option of using CharmCeph and charmed MicroCeph to bring Ceph into infrastructure. What else? Why consider Ceph over cloud storage? Well, it depends, right? If you have an application that's kind of small or it's new, you don't know how it's going to grow, then something like public cloud infrastructure is awesome. You can sign up with a credit card and kind of off you go. You've got not quite limitless compute and storage, but you've got something that is very scalable and can be used in that phase of growth of a new application. But typically what we see, and we see this really often, is people have like grown up in the cloud and they realize once they get to a certain point, actually, is there a financially better way of doing this? So one of the studies we've done recently, and I'll share a link to a white paper after I've been through all of the questions, is looking at like the cost of storage in public clouds. Once you get to like a certain capacity, it almost becomes so expensive that you can actually build your own infrastructure either adjacent to a public cloud, still use the compute offerings, and use things like Direct Connect or Express Route to reach a co-located storage system kind of nearby. Or if you have your own on-premise data center, or you have the scale to kind of justify that investment, it makes a lot of sense to kind of move out of the public cloud. So yeah, I'll share a link to that in the announcements of the webinar in a few minutes. Some hardware things, single CPU versus two CPUs. From an ease of use point of view, a single CPU, one NUMA region, it's nice and easy. You don't have to worry about any kind of interconnect between those two CPUs in the server. But also being kind of realistic, there are lots of offerings out there that add two CPUs. So you can use things like pinning to tie certain services to each CPU. You can kind of look at where your network card is, and which PCI lanes that is on, and which which CPUs like the local controller for that for those lanes. So with some care, you can kind of balance around some of those more tedious things. A large server is bad. You only mentioned 1U and 2U servers. So this is like another yes and no. Imagine the situation you've got maybe a petabyte of data you want to store. You can quite easily fit that into a single chassis these days. Then you need to think about replication. So say you have 3, maybe 4 servers, so you have like that good operational experience. So you go with as little as possible, and you stuff all of this raw data into a small number of servers. As soon as one of those servers fails, you're losing quite a significant proportion, not only of your capacity, but also the processing power that also goes along with that. So things like rebuilds will take longer because there are less members in the cluster. The other challenge is, when you start looking at those kind of ratios of performance need of a CPU to number of OSDs, you start having to look at very, very high-end CPUs just to get enough resources into those kind of boxes. There is an area where those systems are quite good. If you turn around to me and said, I need to have a capacity of 25 to 35 and beyond petabytes, and you would use these 1 petabyte systems, that's pretty reasonable. You think about the amount of capacity you would lose, or capability that you would lose, if one of those devices was to fail during operations. It's a much lesser impact than when you only have like 3 or 4 in a kind of minimal configuration. How well does Ceph actually scale? So I will kind of break this into 3 bits, I suppose. So if you think about RBD, RBD is the block storage piece of Ceph, and as we scale up a number of nodes, the number of endpoints also scales up, so it is very, very scalable. I saw a comment on LinkedIn about having like the slowest member in the pool, and of course, yeah, it's if you have multi generations of servers and your data in the pool and then subsequent PGs underneath that are spread across like different classes of hardware, there's always going to be a portion of the workload that's going to be serviced by that kind of older generation hardware. I suppose you also have to be realistic that over time hardware is going to change, and also from a financial point of view, you can't just throw away the old stuff. A finance team just won't allow us to do that. So yeah, you're always going to end up with some kind of like imbalance, I suppose, but it's operationally it's fine. So then CephFS data path is very similar to RBD's. So from a scaling point of view, that's a great story. The other area, it is interesting so the other piece of CephFS is the metadata server, so the MDS. The MDS still has some pieces of code in there, kind of single thready. So having some dedicated servers used specifically for the MDS processes with very high clock speed CPUs, not necessarily a large amount of cores, that really, really helps. And then also having lots of RAM available there. There are lots of metadata transactions going on, so the more that can be cached in the MDS, the better. You don't then have to go back to the underlying Ceph storage to retrieve metadata. So that can certainly speed things up. Finally, Rados Gateway. So Rados Gateway is interesting. There's a bunch of different ways of improving the performance of Rados Gateway. One way that we've seen good success with in the past has been to have the Rados Gateway daemon running on every node in the cluster. In some scenarios, you might not want to do that. There is certain like security sort of aspects you might want to think about. If you imagine the Rados Gateway is being used a bit like a proxy, having that sort of separation of dedicated Rados gateways above a Ceph cluster, that can give you a good security stance. So sometimes people do it that way around, but really it's just about making sure that the resources for Rados gateway are available wherever you deploy it. So yeah, if you scale out, you still need to have a chunk of resources available to use it. You can't just kind of add it to an OSD node for free and kind of get away with it that way. If you break it out into physical servers, then or dedicated machines, again, they have to have enough resource in there to run the processes, enough memory, They're kind of stateless, so there is not really any real disk requirements needed in a wireless gateway. But yeah, definitely, making sure there's enough CPU and RAM for the web front end process to run is important. What else? Talked about this one. So CPU. Okay, let's have a look at LinkedIn. Let's see what else has come in. Talked about the slowest member. Section of my system is slower than the other sections due to location is going to run at a slower speed. Okay, so if you have a Ceph cluster that's spread over several locations, there is a feature in Ceph which allows you to do stretch clusters, and of course, you're going to get a different kind of performance behavior, than a cluster that's all in the same location. So yeah, of course, if something is in another place, it is going to cause another kind of performance imbalance. So it's not necessarily recommended to do things like that. Using Ceph's inbuilt replication features is kind of useful. Thinking about object storage and Redis gateway, multi-site is really good. It's a great async solution to having objects stored both locally and also in a remote location as well. Looks like everything from LinkedIn. I will double check after we sort of wrap up the recording, and if there's anything that needs further comments, I'll comment on those directly. And then I guess the last thing is just to post that link I mentioned. So give me 1 second. So I just posted in the announcements a link to it's both actually a recording of a webinar and also a white paper. So this is that kind of explanation around whether it's more cost effective to use public cloud or a private cloud or private storage solution, and that can augment public cloud as well. In the cost analysis in the white paper, it's actually like a fully managed service. So it's something you can just treat as like a public cloud service. Of course, you have to think about things like capacity planning. A little bit more hands-on there. It's not just expect it to continuously grow, but it's certainly something that is definitely worth considering once you have a number of petabytes of data stored in public clouds. And with that, one last check of the Q&A. Okay, there are no more questions, so I'm going to wrap up here. Like I said, I'll check LinkedIn just in a second, make sure I've not missed anything. If there is, I will make comments directly on that. So thank you all again, and I hope the webinar was useful.